All right. Good morning and good evening, everyone. Today I'm Jingfeng Zhang, a researcher from Reckon EIP. Today I'm going to host the 11th TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Reckon EIP to our valuable guest, Praneeth. The full name of Reckon EIP is Reckon Center for Advanced Intelligence Project. EIP was founded in 2016 as a research center for the next EIP project. EIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. EIP aims to enhance the AI's fundamental technology and its real-world applications. We encourage the collaboration with various researchers and engineers in related fields. We will be very grateful if you could visit us in our Nihonbashi office in Tokyo in the near future. Today, our guest, Praneeth, is currently a PhD student at MIT. His main research page is praneeth.mit.edu. His research focuses on developing algorithms for distributed computation in statistics and machine learning under the constraints of privacy, communication, and efficiency. He won the Meta PhD Research Fellowship, was selected as a SERC Scholar, Social Ethical Responsibility of Computing Scholar by MIT Schwarzman's College of Computing, a Baidu Best Paper Award at the NeurIPS 2020, and SciFair and Mark Best Paper Runner-Up Award at IEEE 2021. He was previously a scientist at Apple, Amazon AWS, Motorola Solutions, and Public Engines, Corning, and various startups, all of which were eventually acquired. Hi, Praneeth. We sincerely welcome you to join us. Please proceed to give your talk.
Thank you, Jingfeng, for organizing such a wonderful seminar. It's been very interesting to see the list of speakers in the past and the upcoming seminars, and I really am looking forward to watching more of these talks. Okay, so without further ado, today's talk is so broadly falls under the very wide bucket of distributed and private computation for statistics, and certainly there's a lot of people also working on the distributed and private ML in today's day and age. So this talk is about more of like computing some fundamental quantities, which are very important. So that's basically correlations of some specific kind, and how do you compute them with privacy guarantees. Okay, so let's set up some context so that it starts provoking some thought to the general audience. So think of the ubiquitous availability of different kinds of devices that do different kind of smart data collection for smart data analysis. So one such device, for example, is the IR camera. In this day and age of the pandemic, IR cameras have been used extensively, for example, in places like airports where there's a very large footfall of traffic. So the primary purpose of the IR camera is obviously to check the temperature of the body temperature and to sense any possibility of fever or any other health conditions that could need a little more attention. So that's the utility side of things. But then if you think about it, the data that's being collected in here it has already been shown that you can do much more than detecting fever. You can use it to detect the heart rate and the heart rate variability of people. People have shown that you could use the same data to, of course, understand the gait of the person, understand the gender of the person, and then, more and more than what it was primarily installed for. So that brings that's the kind of like the visionary or like the story that it's bringing in today, right? On one end, people are collecting digital data at a very large scale, and this is the era of big data, certainly, for different choices of what their utility or use cases are. But at the same time, what's happening is the same data leaks a lot of other information, which may or may not be the original intent of the person collecting the data. So this is the issue where there's always a utility privacy trade-off, and how do you, live in, how do we build a world for ourselves where you can achieve the utility you need to while making sure the privacy is not lost. And certainly it's easy to say than done. So that's the setup. And in today's world, it's not just an IR camera. You have all sorts of devices, right? Right from your smartphones that you use in your home. So this is the ecosystem, right? So there's like a lot of devices, and then there's some hubs, and there's some computer networking that goes on. Sometimes there's also like a centralized server, which is a larger entity where the data gets siloed or centralized, like in a data center, for example. So how do you effectively enable individual and organizational, regional, national, and global collaboration through data and intelligence sharing without infringing privacy, security, safety, trust, and regulation? So that's the primary question. And then how do you even incentivize this? If that could be done, how do you incentivize it? Like, so that there's no privacy paradox where if you survey people and ask them if they care for their privacy, they usually say they care for their privacy. But then for some unforeseen reason, they end up giving away their privacy knowingly or unknowingly. This is happening because in today's world, we've not figured out how the whole ecosystem of this kind works with privacy enablement while also giving utility. So you might end up doing something where the person may unknowingly give up their privacy. At the same time, these devices also interact under several topologies, right? You could have interaction in a centralized setup like this, but there's a centralized server with which the devices are interacting. You could have like a decentralized or like a P2P setting. There could be some sort of a hierarchy. There could be vertical partitioning of data where you have the same data samples collected, but each client has different features collected for those same samples. You could have something called split learning that we also do in our group, so on and so forth. And there's federated learning, which is in a typical sense falls under the centralized setting, but people are also studying decentralized P2P learning and are beginning to do that. All right, so this is the utility privacy trade-off. You want to ideally be on the top right, gain as much privacy as possible while also getting as much utility as possible. So how do we get there? And this is a real problem. This is not like this is a problem which would create a lot of societal impact if solved. If you just start listing down like notable healthcare breaches, for example, there's just one kind of breach. These are just a few of those. And as you see, every breach has resulted in millions of victims being affected in terms of their data being breached. And even if you put in like a very small amount per victim, it will blow up into a very large number for the company. At the same time, it's not always about money. There's even more important issues like ethical, moral, legal, trust, and like PR repercussions that's even hard to quantify in some sense at times. So there's going to be a lot of follow-up effects. So how do we solve this problem? So that's the landscape of the domain of work under which some of my projects are falling. I don't want to detail every single project, but we'll be going through the bottom left, which is how do you estimate nonlinear correlations in this kind of a setting? Okay, now coming to the correlations aspect, let's just use a guiding question, for example. This is just an example to walk through. Say you want to measure correlation between somebody's socioeconomic data, so everything about their income, social status, ethnicity, and so on and so forth. And you want to measure the correlation of that socioeconomic data with, say, health status or like disease status of the people. So how do you measure people's, or let's make it even more scarier from a privacy perspective. How do you measure within socioeconomic data, let's pick, say, like banking transactions. How do you measure correlation between their banking transactions, which are certainly extremely private, and their healthcare status, which is also their health records, which are also extremely private? And how do you do that without leaking privacy? At the same time, correlations are such a foundational concept since even Carl Pearson and Fisher have started the field of statistics over 100 years back. So this measuring it without privacy is not as much of a concern if the whole world was living on just one device, but that's extreme. So if everything was on device, then you don't need a solution because everything is on the same device and the correlation is computed on device and you never release the correlation, then you're okay. But if you want to release the correlation, then you have the privacy constraint because you want to, even if it's on device, you need to have some way of formally adding privacy. So that part has been studied recently of how, if the data is on device, how do you do it? But then comes the question, let's move from one device to say two parties. So you have data is on two parties, two devices, or say two hospitals or one banking company, say like a banking company and a hospital, for example. So how do you measure the correlations between these two parties at this time where you don't want to leak the privacy? That's when it gets even more interesting. And of course, a starting solution would be like anonymize the data, but it's been shown again and again that anonymization is not enough. Even the slide where I was showing a lot of breaches, of course, the data was anonymized, but there was leaks that were happening. So anonymity is not enough in today's world to prevent privacy leakages. So what are other hammers you could use? One of them is about adding noise, or it's also kind of, you can also think of like randomization of the computation at different stages of the computation. How do you randomize the computation to some extent so that you end up getting privacy? And what is the kind of privacy we're looking for? There's a definition of privacy, of differential privacy. So it's a mathematical formulation of a definition of privacy. And there are different mechanisms that one could use, and as long as you can prove that that mechanism reaches the guarantee of differential privacy, then you have differential privacy and the properties that differential privacy allows for. And certainly there's always going to be a privacy utility trade-off, and sometimes the trade-off is very favorable, and many other times the trade-off is not favorable. What I mean is you end up getting high privacy, but then you might lose a lot of utility in what you really want to compute. So the North Star, for example, is can you do like sublinear error in maybe sample size or dimension and stuff like that in measuring correlation, nonlinear correlation, while also ensuring differential privacy is preserved, right? That would be like an ideal place to go to. Okay, and then now we're coming to the multi-party setup, right? So there's a single party setup, there's a multi-party setup. We're talking about distributed and private, if you remember my first slide, right? So let's talk about the distributed aspect. That's why I'm referring to the two-party problem. So you could have a single party correlation problem where all the data is on the same device, and then the querier is outside the ecosystem of this device, and he or she would like to know what is the correlation between features X and a set of features Y, both of them that lie on the same device. So that's a single party problem. But what I am going to be talking more about is the two-party problem. So there is data about features X. So this could be socioeconomic data on a client 1 on one device. And there is data about features Y on client 2 on another device. And then how do you measure the correlation between X and Y without leaking the privacy of either of the parties? And within the two-party correlation problem, I'm also restricting the kind of communication that I would be allowing for. So the only communication that I would allow for is one-way communication. So that's what this arrow is showing. So there's going to be only communication allowed from device client from client of client 1 to device held by client 2. So what that means is whatever communication goes out is some sort of intermediate computation involved in reaching your final goal, which is measuring the correlation itself. So the intermediate computation that goes out needs to be privatized so that once the intermediate computation goes into device 2, then client 2 can finish the rest of the computation and post-process that intermediate computation further, and then it gets the answer. And client 2 gets the answer of what the correlation is between Y and X, but it never releases the answer back to this guy or anyone in the public. It just makes it does internal decision making, but it never releases the exact answer. So you can think of like a data buyer and a data seller, for example. And a data seller would like to know how their data is correlated with some potential data buyer, and so on and so forth. So that's another setup. And then, of course, can we get sublinear error? That would be a great thing, while preserving privacy, right? So this is the data seller, data buyer kind of a use case. But correlation is so fundamental that, I mean, it's become like a common word even in non-technical discussions. People use the word correlation in day-to-day life, regardless of whether they're doing advanced statistics or not. So we can always come up with many examples of why you want to measure correlation between data, and in today's world, data is also distributed. So how do these two things come together, and how do you measure it? Okay, so I said it's a common word, that's fine. I mean, we could use it in our common general discussions, but let's also understand why it's an important problem in the technical world, right? On the technical side of things, it's some sort of a root problem. If you can privatize correlation in the two-party setting, there's many other leaf problems that depend on this problem being solved. So if you can do this, you can solve you can directly solve a few of the downstream problems, or you can at least partially solve the downstream problems. But this is a piece that definitely needs to be plugged in for these things to work, even if you want to solve it completely. So this is a partial piece that needs to be plugged in. So let me list a few of those. So if you can measure correlations between, say, two parties or multiple parties, let's say focus on two parties to keep things simple. You could also do hypothesis testing, specifically for testing independence between two parties. Because if you have a right measure of correlation, nonlinear correlation, what that is really measuring is on one extreme whether the data is dependent, or on the other extreme whether the data is independent. So instead of doing a point estimate of just measuring the correlation privately, you can also do hypothesis testing and do independence testing to answer or to reject or not reject a null hypothesis of independence. So how do you do that with high probability of confidence? So that really depends on privatizing correlation, because the test statistic for independence testing, for example, there are many of those. One of the important statistics is a ratio of the correlation itself, or like it is the covariance, which is the unnormalized version of the correlation itself, and some other function of distances. So you want to privatize the numerator, which is literally coming from this part. So if you privatize correlations, this is important. This can be partially solved. And then when you privatize the rest of it, all of it is done. Similarly, you could do causal direction estimation between two variables at a time. So does X, is the causal direction from X to Y or Y to X? And this also depends on this root problem being solved, right? Because one way to do it, for example, this ICML paper is to regress Y from X and also to do a regression of X from Y. So you do regression both ways. You look at the residuals, and then you measure the correlation between the residuals and the covariates itself, the input features. You do that for both regressions. So because you're doing two regressions, you'll have two residuals. For both sets of residuals, you can measure correlations with respect to the corresponding covariates. And then they literally look at which regression's correlation is more than the other. And the one with the greater correlation is going to determine what the direction is. So whether X is causing Y or Y causing X. So all of this depends on a bunch of things. Doing regression privately, people have been working on it. And then you do some residuals, you may lose some privacy at that point, even if your regression is private, but then you also have to do this final step, which is measure correlations between data in a private setting. And this thing literally falls in the one-way setup of two-party private correlation estimation that I was showing in the previous slide. So this is another reason why this is important to solve this downstream problem. You could do data synthesis in a private way in a multi-party setting. So you can seed copula models with, and typically to synthesize data with copula models, even in the non-private setting, you need to feed in some estimates of correlation. And the better the estimates of correlation, the better it is. But if your data is distributed, you need to estimate it in a distributed way and also with privacy. So if you can do this thing, you can feed in better correlation estimates privately, and then you will also have multi-party data synthesis, which is very cool. You could do feature screening, feature selection, because these obviously depend on estimates of correlation. So this is like feature selection with guarantees, basically. It's not with heuristics, but with like probabilistic guarantees and concentration bounds. So this is just reasoning for motivating why this is an important problem, even technically, apart from everyone using the word correlation in a general setting or like in a social setting. Okay, so there's different ways one could go about this. So the main aha about the attempt that reasonably works is as follows. I just want to give away the aha, and then we go to the details in a more like a step-by-step basis. The main idea of the aha is random project. Take your data set, the private data set, and then compute like either a specific graph Laplacian of your data, which is basically understanding the neighborhood structure of your data as if each sample is in a graph at a node. Either model it as a Laplacian, as a graph Laplacian, or model your data using covariance or a specific style of covariance, if not even the linear, if not just the XX transpose, you could do some sort of a featureized version of it, doesn't matter. And then do that, and then random project the Laplacians or the covariances instead of random projecting the raw data. Typically, of course, random projections are used on raw data, but here, random project this matrix. What does it mean to random project a matrix as opposed to data? I mean, a square matrix of this kind, like the structured matrix like covariance. So you basically hit the covariance matrix with the random matrix, both from right and left. So you do something like if R was your random matrix, XX transpose was your covariance, then you do R transpose, X transpose R, something of that sort. So you hit from both sides. Once you random project the covariance of your data, we showed that you can express the nonlinear correlation, which is what you wanted to measure in the first place, you can express that solely as a function of that corresponding Laplacian or covariance. Okay, so what this means is you have to random project the Laplacian many times, and every time you can express the nonlinear correlation as a function of that random projected Laplacian. You take the correlation between the random projected versions of these Laplacians instead, right? Because correlation is a function of Laplacian. Now you have a random projected version of the Laplacian, you use that instead as a proxy instead of using the original Laplacian in this original function. So now nonlinear correlation is a function of a randomized Laplacian as opposed to standard Laplacian. And this is a better idea in achieving better error bounds as opposed to adding noise directly on the data itself or projecting the data itself and then adding noise. People have shown roughly in 2012, Avram, Blum, or Shafet, Jeremiah Block et al., that random projections in general, even if you random project your data, it provides differential privacy. But if you want to get better utility, a better route is to project it in this form through the Laplacian as opposed to the raw data, at least for the nonlinear correlation query. Right, so little pictures. These are just cartoon pictures. This is not the high dimensional real data or like socioeconomic data, at least in this slide. So don't try to read through the graphics within the plot. This is just a block here for just showing the stages. So in a non-private setting, the question is, even if you express distance, the correlation that we use is called distance correlation. I'll give you a shorter survey of different kinds of correlations later, but distance correlation is a reasonably good nonlinear estimate of correlation, of nonlinear correlation. But then the question now is, I said nonlinear correlation can be solely expressed as a function of Laplacian. This is in the non-private setting. But then what if you start doing random projections? There's no guarantee unless you prove that a random projected version of Laplacian is also a reasonable estimate of nonlinear correlation. Even in the non-private setting, even if the goal was not privacy, is it a good estimate in the first place? So that's what we're showing here. Even in the non-private setting, when you random project the Laplacians and use the function expressed as part of the random projected Laplacian, and if you compute if you do like k random projections, and if you compute the nonlinear correlation, which is called distance correlation, it's just the name of one kind of nonlinear correlation. If you compute that on the random projected version, if you do that all k times, so every time you do a projection, you compute the corresponding correlation. And then you take the average of the estimates of correlations. This has already been shown in the non-private setting that it's a good estimator. Firstly, it's an unbiased estimator of the original distance correlation, even if you're doing random projections. And the original distance correlation doesn't need to do random projections, just saying it. So this is a good estimate of that. At the same time, the deviation is well concentrated, right? So the variability is not too high. So this is a good starting point because people have shown random projection has privacy benefits. And if you project the right thing, you get better benefits instead of projecting the raw data itself. At the same time, it also has estimation benefits because even in the non-private goal, it's a good, it kind of aids estimation if you do it a bunch of times on average stuff. Okay, so let's keep going. What about the private estimator? So we're in the one-way setting, so only X needs to privatize because Y never releases the final answer outside, or Y's data never goes out, or any computation of Y never gets released. Only intermediate computation of X gets released, right, of the first climb. So if you even add noise after the random projecting the data as opposed to Laplacian, you would get some, your estimator would look like this, just like previously, but every time after the random projection, U case and V case are the corresponding random projections. You're doing K of them. And these are some normalizing constants that are required. And this is the distance covariance function, correlation function. So if you do add noise, even after random projecting the data, as opposed to the Laplacian, which you'll see later, because this is like a 101 solution. We started with 001, this is going to 101, the next level. Now the question is, what is the privacy guarantee? So this does satisfy differential privacy, which we can show exactly how much and how the amount of noise you add is going to trade off the amount of privacy you get. So how much noise needs to be added in order to achieve differential privacy of some level can be shown. And then we need to know what the estimation error is, like, because you're adding noise, like now what's happening? Because you're not only random projecting, you're adding noise to make the random projection even more private, for example. Because if you project to much lower dimension or much higher dimension, things change. There's different dependencies on the dimension you're projecting, the sample size that you have, the epsilon and delta, the privacy parameters that you're requesting. So let's start in this order. What is the privacy guarantee that we're looking for? Differential privacy. So what is differential privacy? Differential privacy says, say you have some data X and take some neighboring data, which is X prime. And what do we mean by neighboring? In the standard sense, people have come up with various versions of it, but the more classical sense, X and X prime are considered to be neighboring if all records between X and X prime are the same. All samples are the same, except for one record. Only one record could change, which means the Hamming distance between the database of X and the database of X prime is 1. Only one thing changes, which means X and X prime are very similar except for one record. Even then, when you apply your query that you're trying to privatize, let's call that M. So you do M of X, you do M of X prime on very similar data sets except one record. Even then, the probability distribution of the output of this query should not vary by much, because epsilon is always chosen to be a small number. Think of it like less than 1. I mean, people sometimes choose larger as well, but it's certainly not in like the millions or anything. So especially when it's less than 1, it's equivalent to like log of 1 plus epsilon 1 minus epsilon-ish. So basically it's saying the output probability distributions don't change much, even if the input databases are just very neighboring, which means it's harder to figure out what that new record is that is different in X prime as opposed to X. That cannot be reconstructed. People come up with the reconstruction guarantees, and that also depends on what query you're dealing with and how many queries the attacker is allowed to make on a database, and it does whether the attacker knows any priors or not. So that's the jump from differential privacy to preventing reconstruction attacks. But at the same time, differential privacy also prevents some other kind of attack without making any additional jump, which is an attack called membership inference, which is to figure out if any given record is part of the input to this query or not. Like, can you figure out if someone's record is in the input or not? And that's what this is protecting, the statement by itself. Now, because the distributions are not changing, the output distributions, whether the record is present or not. Now, what is delta? It's just a slack parameter. It's a small number, which is the probability under which the guarantee of differential privacy doesn't hold. It's like a slack parameter. And people can also choose delta equal to 0, then that's called pure differential privacy, because there's no slack for error of leaking privacy. But otherwise, it's if you use epsilon and delta, epsilon is the privacy level and delta is the slack level, slack parameter, right? If you use both, then it's called approximate differential privacy. And there are mechanisms for both kinds, pure and approximate. So for the specific query I was showing here, if you do random projection and add noise and then take the correlations and do k of those random projections and average the correlations, this is the amount of noise you need to add that depends on epsilon, delta, and some other parameters. We show a concentration bound in terms of the estimation error, which is the third question. Is the estimate still going to be fine? The probability is very tight, but then of course, depending on what you're feeding in and how your setup is and how many random projections you're doing and to what dimension you're reducing your after the random projection, if you're reducing dimension, how low are you reducing dimension, things like that, and your choice of privacy parameters epsilon delta, you have so and so dependencies. It's okay. I mean, it's not bad. But then can we, instead of settling for mediocre, can we start pushing this limit further? So we did this result, and then we started thinking some more. And the thought that helped us, so I'm not sure if you guys have heard of Game of Thrones, but it's a popular series that came out of a very popular book series that became a very popular TV series. Right. So, but the point is not to talk about the series, but to talk about the second phrase that I said, which is strategic map of allies. So Game of Thrones is, yeah, so I see some thumbs ups about Game of Thrones. That's good. So, but the point is in Game of Thrones, there are different kinds of kingdoms and there is always a strategy involved, right? This is like a game theory with kingdoms and, wars and fighting involved and resources. And sometimes it's hard to figure out who your ally is, but if you really know who the real ally is, you can always use it to your favor. But of course, this is in the real TV series, sometimes people that are not allies pose as if they're allies so that they can backstab a kingdom. Or maybe there are people that are allies, but somehow they show up, maybe they are perceived as being an enemy. So either way, so the bigger philosophy here is, we have a problem at hand. Let's think of it from a Game of Thrones perspective. And there's different aspects involved with solving our problem in different entities. So we want to figure out what are the strategic map of LIs of what are the problems that if solved is going to help our problem being solved better, right? Because we have one solution already, but how do you do better, right? Because our original solution involved random projecting the data and then adding noise or just trying to create the data, for example. I said the AHA was about projecting Laplacians or covariances. So this is what I'm showing. So Laplacians are LIs, but we need to understand the full picture. So there are two kingdoms here. One kingdom in Game of Thrones for us is the private correlation country, the kingdom of private estimating correlations privately. The other kingdom is a very neighboring kingdom, which is the independence testing. How do you do hypothesis test of independence privately? So these two kingdoms are very adjacent, which means they're neighboring. There's a lot to borrow and learn from each other about these problems, but there are some common aspects. So let's go through some of these. So there's data, of course, involved. You can express distance covariance as a function of a Laplacian, which is what we showed, a specific graph Laplacian, not any graph Laplacian you come up with. So since you can express a distance covariance as a function of Laplacian, if you build that Laplacian, you can estimate distance covariance. At the same time, people have independently studied how to privatize Laplacians, not specifically distance covariance Laplacians, any Laplacian. So this is a more generic result, although this is a specific result. A specific Laplacian built from data will give you an exact estimate of distance covariance. But any Laplacian that you build can be privatized. There are people have studied, because Laplacian is just like another fundamental quantity like correlation or covariance. People have many downstream benefits if one could privatize graph Laplacian. So people have studied that independently of different mechanisms to privatize with respect to differential privacy. At the same time, if you privatize a Laplacian, and in addition to that, if you also can privatize the average of all pairs of distances between your rows of the rows of your data, if you do both of these things, then you're done with respect to the independence testing problem. That is all you need to estimate the to express the test statistic used in hypothesis testing. But anyway, so this is the extended part. Is not immediately important on the correlation side, but let's go to the correlation country, the private Laplacian or the private covariance. You can do the same thing either with a Laplacian or with a covariance. So either way, if you privatize a Laplacian or a covariance, there are many downstream queries with which you would get sublinear error in estimating the solutions to those queries that depend on these Laplacians. So you can privatize Laplacian, and then differential privacy has a beautiful property called the post-processing property. If any downstream query of a privatized entity, which is differentially private, if any post-processing does not need to access the raw data, but just need to access just the privatized entity, then all of those queries outputs are also differentially private. That makes differential privacy very attractive. It has this post-processing guarantee. Your post-processing of a private answer never loses privacy, as long as the post-processing is just going forward and not going backward and collecting the data again. Therefore, this being a central quantity, you can do graph cut queries with privacy. You could measure what is known as a directional variance query with privacy, and the list goes on, because Laplacians are very useful. But when I say the list goes on, whatever you do with the Laplacian will not guarantee high utility, as in like sublinear error, or like you cannot do everything with the privatized version of Laplacian with very high accuracy. You can do some things. And some of those things that you can do with high accuracy, where you can achieve some sort of sublinear error and then no dependency on sample size. So you can have millions of samples, the error is not going to increase, but it certainly has a dependency on the dimension, for example. Let's say like K, for example, of your data set. And then even that dependency is sublinear logarithm. So, and it depends on how many queries you're doing as well. But anyway, so the good queries for us, some of the good queries where you can reduce your problem into some function of a nicer set of problems which behave nicely, are the cut queries, and especially the directional variance queries and the cut queries. So in our case, we don't care about the cut query as much, but we are in the correlation country, and that's what this country cares about, how to do correlation well. So we care about the directional variance query because we also show that distance covariance can not only be expressed as a function of a specific Laplacian or a specific covariance, but it can also be expressed as a function of a sum of specific directional variances. So if you can do directional variance queries, if you can do K of them, say if your data had K columns, forget about the number of samples, doesn't matter if it has K columns. If you can estimate this quadratic form where I is the column number. So any of the sum end in here is called the directional variance query. So this is a directional variance of column number xi, of column xi, with respect to a covariance matrix, say BB transpose. But if you plug in the right covariances or the right things, right Laplaces in here, then even then it's a directional variance query. And we show that distance covariance, which is the unnormalized version of distance correlation, is just a sum of directional variance queries of its different columns in the data, which means we can get sublinear error if you privatize, if you can express your inner matrix, because your privacy always with respect to the inner matrix in the directional variance query. If you can express the inner matrix as a function of your data and the outer matrix as a function of non-private data, which we show, because we show in our paper that you can do that. And in that kind of a formulation, all you need to do is privatize a Laplacian, and then you have to do k independent sums of directional variance queries, and you will get, depending on the number of things you're adding, you would get some sort of sublinear error. And of course, I'm ignoring in the slide the exact constants and the polynomial terms and things like that, which you will see in our drafts and stuff. There are two drafts. One draft is out. The other draft is going to be out very soon. It's in this thing. So this draft is going to deal with the starter bound. And then we're also updating the draft again. And this other draft will be out very soon. We'll show you the sublinear route that we're talking about. Okay, so that's the way to solve this problem in a reasonable way with reasonable guarantees. Now let's deal with, so we figured out, I gave you the aha, I gave you how the meat of the problem, how things are working, and that's the trick basically. Now let's come to this, let's take a, let's come to some of the secondary elements of this, and also let's take a higher level view of the other things involved, the rest of the actors involved now, the smaller actors in some sense with respect to this particular topic, but they're still equally important. So what is distance correlation in the first place? I said it's a measure of nonlinear correlation. And of course, there are many measures of nonlinear correlation, but so what is this measure exactly doing? Some trivia. Distance correlation comes under a sub-area of statistics called energy statistics. And some trivia is it was introduced by a person called Shekeli, Gabor Shekeli, in today's world. And he was a student of Alfred Renyi, who's extremely influential. Renyi was extremely influential in many areas of information theory and statistics. And he has a university named after him in Hungary. So that's trivia. Now coming back to what this measure is really doing, it's kind of similar to mutual information, but let's be exact. So what it's measuring is, if you have a joint distribution, what is statistical dependence or statistical independence? So let's define statistical independence. Statistical independence says, if you have a joint distribution of random variables x and y, and if you can write it as a product of marginals of x and y, then x and y are known as to be are considered to be independent or statistically independent, which means distance covariance, the unnormalized version or the numerator, is measuring how far is the joint distribution of any two given random variables from being written as a product of its marginals. That's what this is measuring with respect to a specific norm, and these are all functions. We'll have specific integrals involved. But then the point is, in information theory, this is the important difference. There are many measures of dependencies between distributions in information theory, which is again a very influential field. But there, the dependencies really depend on the probabilities, just like in this function. Like you measure those, you write those dependencies as functions of probabilities, joint probabilities, marginal probabilities, conditional probabilities, blah, blah, blah. The issue with writing things with probabilities is, although it's very beautiful, is when it comes to estimating joint distributions in high dimensions, it's not trivial. It's not easy to estimate distributions in high dimensions. It's okay to do it in 1 or 2 dimensions. So the benefit of distance covariance or distance correlation and energy statistics in general is the follows. You don't have to estimate probabilities, but you can still measure this kind of probabilistic notion of dependence. So how is this happening? So this is how statistics works, right? So this is the population notion of what you would like to measure. But there are statistics involved which can estimate this population notion, which are the statistics, which are the energy statistics, which think of it like a kitchen sink where you can throw everything into it. It's a good kitchen sink and it'll crush things down into the trash or whatever it's supposed to go to. So the thing is, there's just you can compute a bunch of functions which solely depend on functions, which are solely functions of distances and just Euclidean distances. And if you measure these different things, if you compute these different things on your data, on your sample data, which are just functions of distances, and do some other functions with that, then you would end up getting an estimate of distance covariance. You can estimate this without estimating probabilities by just working with Euclidean distances. So that seems magical. But people have shown that these are biased statistics of this measure, and they also come up with unbiased versions of it. But in the end, all it ends up doing is compute some bunch of Euclidean distances and do some formulas, and then you will be able to estimate this beautiful probabilistic notion in an unbiased way with good concentration bounds. So that's that. So that's distance correlation. And of course, as correlation is fundamental, for that reason, people have studied many ways of measuring dependencies between distributions. So we talked about energy statistics, the distance correlation, the unnormalized version is called distance covariance. There's Brownian distance covariance, partial distance correlation, blah, 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 conditional distance correlation. At the same time, there's another set of popular things, dependencies measures, which we can call as kernel covariance operators. There's constraint covariance. The Hilbert-Schmidt independence criteria is very popular. Kernel target element, these are popular. There's integral probability metrics like MMD. Even people in the deep learning era use a lot of MMD, HSIC distance correlation, things like this. And kernel methods, also people were using these kind of things. There's Wasserstein distance, very popular in optimal transport problems, so on and so forth. And then, of course, there's this huge area of work around information theoretic measures. There are many, the list keeps going on. It's hard for me to list all possible dependencies measures that information theory comes up with. So this is a quicker survey. And what I showed you is how to prioritize distance correlation. At the same time, since these things are of active interest to many people around the world, people have also started finding connections. People have shown that, for example, HSIC, distance correlation is a special case of HSIC, where distance correlation doesn't require any tuning parameters, although HSIC requires tuning parameters. And those are again special cases of kernel target element, and these are again special cases of maximum mean discrepancy. And I'm not aware of many results that connect these families with information theoretic measures as much though. So that's an interesting thing. If you're working on just dependencies measures, connecting any of these with information theoretic measures would be of interest for sure. I mean, you can connect them under simplistic settings, but broadly have not been connected, just as these things have been kind of connected reasonably. So that's coming towards the end of the talk. I told you why there's a central problem. We worked on it, and we are working on this, and we're almost done with this part as well. And I'll be working on some of these other aspects. And if you have other interests of where you could apply private correlations, you feel free to reach out to me. Again, some other secondary aspects is quickly in one of my last couple slides is I said one of the downstream problems that can be solved if you solve this correlation problem in a private way in a multi-party setting is the private multi-party independence testing problem, or like the private two-party independence testing problem. How do you do independence testing, like hypothesis tests, right? So what is a classical way in which hypothesis tests run, right? So basically this is again a 001 explanation, not even a 101. So, but this is the overall landscape. Now, one popular way of doing simple hypothesis testing is you first state what your null hypothesis is, you state alternate hypothesis. You want to test with high probability which one, whether you reject or not reject the null hypothesis. So the way they do it is they say, if you want to measure this, they assume that to make this decision, they assume that the null hypothesis is true. Condition on the fact that the null hypothesis is true, they assume that, and they come up with some statistic that they can compute on the data. But then they also prove that if the null hypothesis was true, this specific formula for the statistic that you compute on the data will always asymptotically, like when the sample size is large, will asymptotically have a specific distribution. So they derive the asymptotic distribution of the test statistic under the case condition of null being true. So then you know what the distribution, the textbook distribution would look like in that case for that specific hypothesis test problem. And then what they do is they ask the user what level of confidence you want in making a decision on whether to go with null or not to go with null, right? So that level of confidence decides what is known as the rejection region for this specific test statistic. Because this is saying if the null was true, the test statistic has this distribution, which means any values in the tail, as you go farther in the tail, if you observe those values when you compute the same test statistic, because this is like the textbook distribution, and then you compute the observed test statistic on your specific data set, And you will know that if the null were to be true, it is very unlikely to observe a test statistic that is going very further into the tail, as opposed to like closer to the central tendency. So based on the level of significance you ask for, you decide a strict or a less strict rejection region. And based on the observed value of the test statistic, if it falls in the rejection region, you reject the null. If it falls in the acceptance region, you accept the null. So on and so forth. So that's the move. But the thing is, the beauty is the independence testing when you do in energy statistics is just the test statistic, condition on null being true. The test statistic is basically just a function of distance covariance, which is what we privatized. And also we privatized correlation, and a denominator, which is again a function of distances. So that's the intricate link of why, if you did nonlinear correlation, you need to do a little more, and then you'll be able to privatize independence testing as well in the 247. So this is that ratio. This talk was about the numerator, and denominator is, let's call that a talk for another day. And then people have already shown that this is the beauty, regardless of what your data's distribution is, even if you don't tell me what the distribution is, even if you don't have an analytical form, regardless of dimension, and even if X and Y have the same set of samples, but different number of features. So X could have 10 features and Y could have like 1,000 features, doesn't matter. It could have different column sizes, even because distances are always between samples. That's the reason things will commute in this energy statistics. Even in that setup, if you compute the ratio of this thing, it's beautifully always gonna follow the normal kind of a distribution. So that's kind of beautiful, right? That's the universe. This kind of universality you end up seeing philosophically in many parts of statistics. Like that central limit theorem is a great example. You do whatever weird thing, but it would end up having like due to the central limit theorem, whenever it holds, you would end up having Gaussian. So that's kind of thing holds here as well. But this is non-parametric. You don't assume any distributions, but even then this thing holds. So that's the test statistic for testing independence and rejecting or not rejecting the null hypothesis of independence, for example, with some high level of significance alpha. All right, so let me close there and then leave this motivating slide here. Yeah, so that's the end of the talk. And let me stop sharing. Oh, there's a lot of people now. Great. Yeah.
Thank you for Praneeth giving us excited to talk about the privacy talks. Hi, audience. If you have any questions, you are sincerely welcome to ask here. You can just open your mic, or also you want to type it in the chat box, fine. Let me have a question during the talk. For example, when we have some kind of data set, what if we have some repeated data? You know, we have some data repetition. If we have repeated data, basically we inherently cannot distinguish whether this record is analysis or not. So what do you think about this? For example, the data repetition things in the data set in terms of privacy?
Yeah, it's a reasonable statement. So I mean, yeah, repeated data happens a lot of times. So were you interested in repeated data for privacy or for estimating just the correlation in general?
I think estimates the correlation in general.
Yeah. So if you had repeated data, your correlation is basically measuring how the distributions are correlated. Yeah. Right. So if you have repeated data, that is just going to trickle down into the distribution itself. If it's heavily repeated, it would end up more towards the mean of the distribution. If it's occasionally repeated, closer towards the tail, but rarely repeated.
Yeah. So when it comes to the privacy, you know, how it affects the privacy something.
Yeah. So privacy, there's an important impact there. There's more of an impact. So the way differential privacy's properties work is as follows. Once you have differential privacy achieved, but then it also, the level of privacy is not achieved forever. Like once you achieve some epsilon level of differential privacy, epsilon doesn't hold forever. It depends on, sometimes it holds forever, but depends on what you do. So if you were to apply multiple queries to the database, to the same data set from which the query is being computed, then there is an effect of sequential composition. The number of queries you do will decide how much privacy you're losing. There's an exact trade-off that has been studied. These are known as the composition properties. And there is a sequential composition. There's also advanced composition properties. So that's where the repeated data could have some influence, because it's equivalent to repeated queries if you have repeated data, depending on what you're measuring. Right.
I see.
Yeah.
Okay. Thank you very much. I got what I had. All right. Also, there's a question in the chat box.
Sure. Oh yeah, I see it. Yeah, thanks for sharing. Yeah. Besides adding noise to balance the utility and the privacy, are there any other approaches to achieve high utility and protect privacy at the same time? It's a good question. It's a high-level question. So there are different kinds of notions of privacy. So if you are talking about cryptographic methods, they achieve a high level of privacy, but of a different kind than what is achieved by differential privacy. So cryptography protects against different kinds of attacks as opposed to the attacks that differential privacy protects against. So if cryptography has some scalability issues, depending on if your compute is very complex, then your protocol will not scale up in compute and communication. It'll take forever. But otherwise, it has a very high level of privacy. But then it doesn't have the same level of privacy that differential privacy has, because they're protecting two different things. The answer is as follows. So in differential privacy, the output of the query is being privatized with respect to the which is privatized with respect to the sensitive input data. But in cryptography, they achieve exact output. They're ensuring the exact output as if there is no privacy involved, which means you get an exact solution. If you do logistic regression, you'll get the exact logistic regression as if you did logistic regression without privacy. And that is the issue, because if you give the exact solution, that's what differential privacy is protecting against. The exact solution, without differential privacy, exact solution is not enough, because that's an identity query and that is going to leak. So to be specific in the lingo, differential privacy protects membership inference attacks, which crypto does not protect against. If you were to release the answer, if you don't release the answer and keep it for yourself, then of course it protects that. But if you never release the answer, you cannot do distributed computation of all kinds. While on the crypto side, you're protecting the computation process itself. You're allowing multiple parties to do parts of the computation, and no party can know about each other's. And then one party will get the final answer, that kind of thing. But if that final answer has to be released to the world, think of like an API that you need to release to the world as a company, then you will not be able to release that with crypto, because it will start releasing the exact answers. The part of the compute will happen in a very secure way, but the final answer itself is leaking privacy. Think of like outliers. If you had a distribution and if there was a bad outlier, and if you release the same thing with and without the outlier, there'll be a lot of difference in the statistic of what you're releasing, whether it is ML or regression or some basic statistic. And that is how the attack works. The membership inference attacks works. So that attack is protected by differential privacy, because it's not allowing you to distinguish any outlier or even an outlier from whether it's an outlier or not. So the outlier is also hidden. So if there is some specific person of a specific ethnicity and gender and age, and if they need a fair evaluation of their data, and their privacy should not be leaked, then if they were an outlier in their data set, and if everything starts changing, that's a problem. So you want to protect the worst case privacy of the output. So that's output privacy. This is more like input and compute privacy. They're protecting different things. Cool, thank you.
All right. Again, thanks very much for Pranay's great talks here, and I'm very excited for answering to our questions. Thanks again for Pranay's give us very excellent talk. So when the situation is lifted, hopefully, if you have time, you can come to visit our Recon Center in the near future.
I would love to. Yeah, I would love to. And then feel free to reach out to me by email. I'm very friendly. Sure. I'm not trying to bite anyone. So I'm looking forward to collaborating. So yeah, have a good one.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.
Yeah. All right. Next, we will welcome our second guest, Ximei.
Yes, I'm here.
Yeah. Hi, Ximei. Can you try your try to share your screen? Check whether it works. Okay. Then meanwhile, I will introduce you to our audience. Ximei is currently a PhD candidate in the School of Software, Tsinghua University, advised by Professor Jianmin Wang and Professor Mingsheng Long. Before that, he received his bachelor degree from Department of Automation, Tsinghua University. His research interests lie in transfer learning, domain adaptation, self-supervised learning. He is an outstanding reviewer for NeurIPS 2020, SAR 2021, and NeurIPS 2021, and also an expert reviewer for SML 2021. We sincerely welcome Ximei to give his talk, Advances and Perspective of Transfer Learning. Welcome. Ximei, please proceed.
Okay, thank you, Jinfeng. Thanks for the invitation. It's my pleasure to share my research at this wonderful seminar. I'm Ximei from Xianhua University. Today, I will give a talk about the advances and perspectives of transfer learning. If you have any questions, you can interrupt me. Okay, let me check. In this talk, I will first give a brief introduction to the two main paradigms of transfer learning, which means domain adaptation and task adaptation. Then I will delve into the challenges and advances of them from the perspectives of transferable normalization and self-tuning, respectively. Finally, I will summarize some possible research directions in this field, in my opinion. Okay, as shown in the figure here, the training set, validation set, and the test set are randomly sampled from the ImageNet dataset, and thus they are independent and identically distributed datasets. However, this assumption may be too restricted to be satisfied in real-world applications. For example, if we want to test the model trained on the ImageNet to a sketch domain, can the model still perform well? The answer is obviously not. To this end, transfer learning is proposed to reduce the dataset shift across distributions and transfer knowledge from a related domain or a model to a target task. The big picture of transfer learning includes the following three types. The first one is covariate shift, which has a shift in independent variables. The second one is a prior probability shift, which has a shift in target variables. The third one is a concept shift, which has a shift in the relationship between the independent and target variables. Today, I will first focus on the first type, which means covariate shift. Now, let me delve into the first form of transfer learning, that is domain adaptation. Given a labeled source data set and an unlabeled target data set, domain adaptation aims to train in a classifier on the source data, but it can generalize to the target domain. Its main challenge is the data set shift across domains. Definitely, for classification task of domain adaptation, the target risk here is error cubed, can be bounded by the source risk. Here is error P. The bounded by the source risk, the ideal joint error, and the disparity difference, in which the ideal joint error is achieved by finding an ideal joint hypothesis at start on both source and target domains. And the disparity difference here measures the distribution shift across domains. Note that the above decomposition of the target risk can be attained by simply using the triangle inequalities. Since the ideal joint error can be ignored at most cases, to achieve a lower target risk, most researchers focus on reducing the disparity difference across domains. Fortunately, the disparity difference can be illustrated as H delta H divergence, and H delta H divergence is a hypothesis-independent discrepancy, which means that it's just dependent on hypothesis space. To reduce the disparity difference across domains, one classical work is Deep Adaptation Network, which is a DAN. It's proposed to reduce the statistical distance across domains at different network layers. Specifically, DAN adopts a multi-kernel NMD as the distance measure. By measuring the moments across domains, it achieves much better performance than the source-only model, and is popular in this field. Another popular work in domain adaptation is domain adversarial training of neural networks, which is DANN. It introduced a domain discriminator to distinguish the source and the target features, while the feature extractor is trained to fool the target domain discriminator. By adversarial training in this two-player minimax game, DANN is designed to generate domain invariant representations and achieve higher accuracy in the target domain. To date, there have been extensive works that tackle domain adaptation by reducing the domain shape from the perspectives of loss function designs, including the series of moment matching and adversarial training. The work in moment matching including DAN, DDC, RTN, and JAN, and etc. And the work in adversarial training includes DANN, MADA, SIPDAN, MCD, and MDD. Of course, all of them are focused on the loss function designs. Today, I will give a new perspective because real attention has been paid to the other side of the coin, that is network designs. Of course, the network design is an indispensable part of domain adaptation. To understand the impact of each internal component on the transferability of the whole deep networks, we delve into the mainstream DNNs, which is ResNet. ResNet is one of the most elegant backbones commonly used in domain adaptation. In ResNet, convolutional layers contribute to feature transformation and abstraction, and pooling layers contribute to enhancing the translation invariance. But some new research reveals that it cannot achieve translation invariance. However, the invariance they achieve cannot bridge domain gap in domain adaptation, since the domains are significantly different. By contrast, batch normalization is crucial for speeding up training, as well as enhancing model performance by smoothing loss landscapes. In batch normalization, it normalizes inputs to be zero mean and univariate, as I showed the equation here, and then scales and shifts the normalized vectors with two trainable parameters to maintain its brightness. The trainable parameters here is gamma and beta. And until it leads, BN shows the spread of statistical moment matching with domain adaptation. However, what will happen when BN is applied to cross-domain scenarios? Before this work, most domain adaptation methods achieved BN in this way. At each BN layer, the representations from the source and target domains are first combined into a single batch, making the mean and variance of the BN layers calculated on this combined batch. In fact, owing to the phenomenon known as dataset bias or domain shift, the difference in their means and variance between domains cannot be ignored. Hence, brute force sharing of the mean and variance across domains, as in the BN layers, may distort the feature distributions and thereby distort the network transferability. Meanwhile, another drawback of BN for domain adaptation is that all channels in BN are equally important in domain adaptation. But some channels are easier to transfer than others, since they contribute to some mode sharing patterns across domains. But some other channels capturing the backgrounds or other irrelevant paths should not be highlighted. So realizing these two drawbacks of BN, how to implement it in an effective way, retaining the simplicity and without changing the other components of ResNet. It's not a trivial. We cannot get a trivial solution for this problem. So here we propose transport normalization in place of existing normalization techniques. First, TrustML has 3 designs. The first one is domain-specific mean and variance. As shown the first equation, it first use the domain-specific mean and variance to normalize the representations. And then it has domain sharing gamma and beta between domains because the domain sharing gamma and beta to update these learnable parameters can be achieved under the supervision of the label source data. The final question is, can we quantify the transparency of these channels in a simple way? This paper gives a positive answer. We first calculate the distance across domains by means, normalized by variance. Second, we generate probability with the student T distribution with a heavier tails. Finally, we use a residual connection to combine the normalized values. Here, someone may has a question about the student T distribution here. Why student T distribution? Through the experimental results, we can show that wait a minute. We can show that it cannot be replaced with softmax or Gaussian transform because softmax is a winner-takes-all strategy, and the size of Gaussian is not that heavy as student T. Only the student T distribution with heavier tails is suitable for highlighting those transferable channels, as well as avoiding overly penalizing the other less transferable channels, but these channels may also informative. So we want to highlight those transferable channels, but avoid overly penalizing the other channels. So student T is more suitable. Okay, as shown in this figure, TrustML calculates statistics of inputs from the source and target domains separately, while the channel transferability is computed in parallel. After normalize, features go through channel adaptive mechanisms to reweight channels according to their transferability. It's quite crucial that the channel transferability strengths shall be evaluated with the status of layer input and assigned to the normalized features. Okay, as a general and lightweight normalization layer, TrustML can be easily plugged into common network backbones in place of the standard batch normalization whenever they are pre-trained or trained from scratch. With stronger network backbones, most documentation methods can be improved without changing their loss functions. As shown in this figure, we can apply TrustML to different kinds of deep neural networks, from vanilla CNN to ResNet to InsertionNet, without any other modifications to the network architectures or introducing any additional hyperparameters. In experiments, we evaluate TrustML on various data sets. As table 1 shows, TrustML enables DNN to surpass methods with more complicated networks or loss function designs. Meanwhile, TrustML can further improve systems, which is a competitive method. Okay, table 3 also demonstrates significantly improve the result of TrustML on Office Home and other data sets. Office Home is much more complicated than Office 31, showing the efficacy of the TrustML on harder problems. Meanwhile, TrustML can be applied to more advanced documentation methods. Here we showed MDD and other network backbones. We also include insertion BN and DTN. And other challenge datasets we include with that 2017. Also, we also compare with more normalization techniques, such as Adaptation and AutoDie. These two batch normalization layer was also designed for documentation, but TrustML can outperform them. TrustML to consistently outperform these two related methods based on either DANN or SIDENT. Further, since Adaptation does not exploit the discriminated statistics of the target domain at training, SIDENT plus with Adaptation performs even worse than SIDENT. Okay, here we also get some theoretical analysis. As showed by Ben David, the learning bound of documentation here is LRT can of a hypothesis H on the target domain can be bounded by 3 terms. The first one is the expected error of H on the source domain, which is LS here, and the A distance, which is a measure of domain discrepancies. And the third one is the error of the ideal joint hypothesis at start on both source and target domains. By calculating A distance and lambda, which is the ideal joint hypothesis error, we found that our TrustML can achieve a lower A distance as well as a lower lambda, implying a lower generalization error by TrustML. Here we give some visualization of domain-adapted alpha. We calculate the transferability alpha for each channel after the training process converges. The channels with the largest and smallest transferabilities are shown in these figures. The channels with higher transferability captured more sharing patterns, such as the textures of objects or the shape, while those with lower transferability focus on the background or other irrelevant patterns. Also, we use the TSNE tool to visualize the representations in the AutoNet layer of ResNet 50. We compare the models with BN and with TrustML we propose based on SIDENT and DAN on task A to D of Office 31. As shown in this figure, the source and target features in models with TrustML are more indistinguishable, implying more transfer features learned by TrustML. Meanwhile, class boundaries are sharper, improving that TrustML has more discriminated features. Okay, in summary, TrustML is a simple, general, and end-to-end trainable normalization layer, and it can improve transferability of DNNs. Also, TrustML can be easily plugged into various DNNs and documentation methods by simply replace their internal BN layers with our proposed TrustML layers. As a general method, TrustML does not introduce any extra learnable parameters or hyperparameters. Also, TrustML improves classification accuracies and accelerates convergence. The code is available at our repository at this website. Yes. Also, I want to highlight that TrustML may be the first one documentation methods that tackle this problem from the perspective of transfer architecture design instead of loss function design. Okay, now let me delve into the second form of transfer learning, which is task adaptation. When fine-tuning from operation model on the target task, where the target task have some label data, but the label data is not enough, so we use the fine-tuning techniques to avoid overfitting. Previous work showed that better ImageNet models usually transfer better. And by linear fine-tuning methods, it's just fine-tune the prediction models and add a new task-specific head to in a new task. Better fine-tuning methods includes learning without forgetting. Learning without forgetting makes the output of the new task consistent with that of the old task to remember as much prediction model knowledge as possible. Also, a state-of-the-art transfer learning method is co-tuning, proposed to learn the relationship between source categories and target categories to fully transfer prediction models. Here we show the test accuracy of co-tuning in the right figure. It shows that co-tuning decreases rapidly as the number of label data decrease. This observation tells us without exploring the intrinsic structure of the unlabeled data, fine-tuning through limited label data is at risk of under-transfer caused by model shift. That is, the fine-tuned model shifts towards the limited label data and leads away from the original smooth model prediction on the large-scale data sets, causing an unsatisfied performance on the test set. Here in the right figure, we can see that with smaller the label ratio, the accuracy of co-tuning is lower. So to avoid the mentioned model shift problem, we can use the unlabeled data. Semi-supervised learning is a powerful approach for addressing the lack of label data, but also exploring unlabeled samples. Typical methods include bimodal, pseudo labeling, and BAT. But recent advances in semi-supervised learning demonstrate that the effectiveness of self-training, which it picks up the class with the highest predicted probability of a sample as its pseudo-label. And self-training has become the mainstream of semi-supervised learning. However, an obvious obstacle in pseudo-labeling is the confirmation bias, which means the performance of a student is restricted by the teacher when learning from inaccurate pseudo-labels. Here in the right figure, we also show that as the number of label data, as the number of the label space enlarged, here is CUB10 to CUB200, the accuracy of this match decrease as the accuracy of the pseudo label, because as the label space enlarged, the model has more probability to be confused by the false pseudo labels. Okay, to escape from the dilemmas of transfer learning and semi-supervised learning and take the power of both worlds, we present self-tuning here. Self-tuning is a novel approach to enable data-efficient deep learning. In this setup, we unify the exploration of labeled data, unlabeled data, and the transfer of operation model. So self-tuning is well believed to have a better performance. So how to alleviate the mentioned confirmation bias problem? We first found that the devil lies in cross-entropy loss, since it focuses on learning a hyperplane for discriminating each class from the other classes. As shown the figure in the right, we can see that if some pseudo labels are wrong, the hyperplanes can be easily directly misled. Also, other loss function includes contrasted learning loss. Yes, but contrasted learning loss underutilized labels and leaving the useful discriminated information on the shelf. As shown the figure in the middle, no hyperplane is learned by contrasted learning loss. So in this paper, we take the power of both cross-entropy loss and contrasted learning loss and propose a new loss named pseudo-group contrast, which combine the advantages of both worlds. The pseudo-group contrast learning loss is raised here to mitigate the reliance on pseudo labels and boost the tolerance to false pseudo labels. Different from the standard contrasted learning loss, which involves just a positive key in each contrast, as showed the equation, the first equation. We can see that only one positive key in standard contrasted learning. And the positive key is a differently augmented view of the same data of the query queue. But in pseudo-group contrast, we introduce a group of positive keys in the same pseudo class to contrast with all negative keys from other pseudo classes. As shown in the second equation, the pseudo-group contrast has a group of positive keys, which is here, including from D is equals to 0 to D to D. Then, why can pseudo-group contrast boost the tolerance to false labels? This is because that we introduce a softmax loss function in pseudo-group contrast. The softmax function generates a predicted probability vector with a sum of 1. So positive keys from the same pseudo class will compete with each other. If some pseudo labels in the positive group are wrong, those keys with true pseudo labels will win this competition, since their representations are more similar to that of Karen compared to the false pseudo labels. And experimental results also showed that with pseudo-group contrast, self-tuning can achieve a much higher performance than this match. And this match used the standard cross-entropy loss. Okay, to further tackle the confirmation bias challenge, we propose a unified font to fully exploit the prediction model M and the label data L and unlabeled data U to tackle the model shift problem. First, initialized from a decently accurate prediction model, self-tuning has a better starting point to provide an implicit regularization that the model trained from scratch on the target data sets. The common practice of semi-supervised learning is trained from scratch, but here we use a prediction model. Next, the queries is shared across labeled and unlabeled data. This design tailors ground truth labels from the labeled data into the shared queue list, thus improving the accuracy of candidate keys for unlabeled queries than that of a separate queue for unlabeled data. Also, okay. Now we can see the experiments and results. In this slide, I only showed one of the tables, and more results can be seen in our paper. As shown in table 1, by unifying the exploration of labeled and unlabeled data and the transfer of operation model, self-tuning outperforms its semi-wide learning and transfer learning counterparts by sharp margins across various data sets and different label ratios. For example, the transfer learning, the result, the first one is fine-tuning. The baseline at 15% label ratio is only 45, and our methods can achieve a much higher accuracy of 60-fold. The first reason is that we also include unlabeled data. The second reason is that we have a much better pseudo-glucan trace mechanism, and also we unify the exploration of labeled and unlabeled data in a parallel way. Okay, in summary, this paper gives a new setup named data efficient deep learning to unleash the power of both worlds of transfer learning and semi-supervised learning. Because semi-supervised learning and transfer learning has a common goal to mitigate the requirement of label data. Also, to tackle the model shift and confirmation bias problems, we propose self-tuning to fully explore the labeled and unlabeled data and the transfer operation model. Also, a general pseudo-glucan trace mechanism is proposed to mitigate the reliance on false pseudo-labels and boost the tolerance to false labels. Also, we conduct comprehensive experiments to demonstrate that self-tuning outperforms its counterparts by sharp margins. And the code is also available at this website. Finally, let me summarize some possible research directions in this field. Okay, from the perspective of standard documentation, since the gap between the theory and algorithm is nearly closing, so this direction, in my opinion, we cannot do too much at this standard direction. But more attention can be paid into documentation in an open and dynamic environment, which included universal documentation, where the classes label space is open across domains, and weakly supervised documentation, which includes noisy labels. And noisy labels will be occurred in real-world applications, and source-free documentation where the source data is not available. So beyond the classification setup in most documentation methods adopt, we can also explore documentation for regression problems and deep regression or single value or dense values regression problems. And also documentation for object detection is a big challenge. Okay, beyond the domain bias, some other bias in transfer learning can be also explored, include task bias, where multitask learning or multi-domain learning both multitask learning and multi-domain learning have a strong applications in recommendation systems in many internet companies. The other bias is model bias. We can further fine-tune the prediction model on the limited label data set. But in our data efficient deep learning, we show that we should also include unlabeled data. So can others, can we propose better fine-tuning methods to fully explore the labeled data, unlabeled data, and the prediction model? So I think the direction of model bias should be also highlighted. Okay, that's all. Thank you. Have you any questions?
Thank you for this great talk. Hi, audience. If you have any questions, or you can directly open your mic to talk, and also you can also type it into the chat box. Yeah. So basically, I have a question in terms of data efficiency. What's your perspective when kind of these things in industry can be applicable in the industry?
Yes. Okay. Let me go back. In this figure, we show that the first transfer learning and semi-supervised learning share a same goal to mitigate the requirement of label data. And in real-world industrial applications, label data is expensive to achieve. By using transfer learning, if we transfer a prediction model to a limited label data set, the model will be easily shift towards the limited label data, and the generalization error will be too high. So by using semi-supervised learning, we didn't explore the advantage of the prediction model. So you will also face the challenge of confirmation bias. In data efficient deep learning, we combine the advantage of these two words and take the power of these two words. I did not have any example to show that it has been implemented in a real world industry. Yes.
Yeah. I
Okay.
see. I see. There is a question in the chat box. You can.
Okay, I will check it.
Yes.
Okay. Some surveys, they organize topics in a similar way. You organize this talk. Yes, today we have too many transfer learning approach and too many transfer learning surveys. In our research group, we publish, not publish. We a new survey is proposed by our teammates. The name is transfer learning. I will check it. Let me check it. I think it's a better survey. The name is Transferability in Deep Learning. It's a survey. Yes, you can search it. I think it's a much better survey for transfer learning. And also, you can go to my advisor's website, Min Shen Long, and he have presented some wonderful talk at this topic, and I think it will be helpful for you. Okay. Another question is, in order to train a time series analytic detection model with few label data between unlabeled data, or including wrong label efficiently, are there any critical methods how to use transfer learning model shape documentation and self-supervised learning? Okay, about time series problems. To be honest, I did not have any experience or in the time series analysis detection problem, but I think the core idea of this problem is the same. We can share the spirit of translearning and documentation, including adversarial training or moment matching. Yes. When we meet with a few labeled data, but we can have enough unlabeled data, we can also use the similar self-training strategy. But how to implement self-training strategy in time series problem may be a new challenge and a new research direction. I think the most important thing is to catch the core idea of translearning, that is moment matching or adversarial training or other classical work. Also, our research group has published translearning libraries. There are many wonderful code at this topic, and you can also search it. I think it may be helpful for you.
Great. Hopefully, Ximei can answer your question.
Okay.
Yeah, if there are no further questions coming up, let's thanks again for Ximei's great talk. I feel very happy I can hear you to give a talk here today. We really hope that the situation lifted, you could physically visit us in Tokyo in our Nihonbashi office in the near future.
Okay. I'm looking forward to go to Japan in Tokyo someday.
Okay, sure, no problem. Drop us in.
Yes.
Okay.
Okay, thank you.
All right.
Bye-bye.
Thank you. Bye-bye. This is the talk. Bye-bye.
Bye-bye.